Welcome to Analysis of Time Series, Chapter 10, Introduction to Partially Observed Markov Process Models. So in part one, we're going to introduce some general ideas for stochastic dynamic systems observed with noise, and the idea of a latent process model and a measurement model on top of that, and the latent process model having the Markov property are going to be key ideas. So uncertainty and variability are common features of biological and social systems, and even physical systems, which ever since Isaac Newton have been modeled using deterministic equations, can also be unpredictable. And in that case, we might want a probability model to describe them. For instance, we can only forecast weather reliably in the near future, so it makes sense to make a probabilistic weather forecast. So by contrast, time series models of deterministic trend plus colored noise of the types we've been looking at earlier in this course imply perfect predictability if the trend function enables extrapolation. So once you've found there's a linear trend or quadratic trend, or maybe trend depending on some other variables, if you knew that trend, then you would be able to predict the time series very well out into the future. And things often are not that predictable. And so to model variability and unpredictability in a practical setting for a dynamic system, it's often helpful to specify a random model for the system, and we call the random model a stochastic model. They're synonyms. Now, oftentimes, we think there are some underlying variables driving the system, but we only have noisy or incomplete measurements. Maybe there are some things we can't observe at all, some things we can maybe get some sort of sample from or some other measurement. And so we model a latent process, and then we model measurements as random variables conditional on the latent process. Now, the latent process can also be called a state process or a hidden process. These ideas have come up in different settings. The latent processes we look at are often going to have the Markov property. So let's talk about that a little bit. So a model for a stochastic dynamic system has the Markov property of the future evolution of the system depends only on the current state plus randomness introduced in the future, but you don't need to know anything about the past. The models with this Markov property are sometimes called Markov chains, sometimes called a Markov process. The term Markov chain is often reserved for situations where either time or the latent state or both take discrete values. The general case can be called a Markov process, and we consider that including Markov chains. And so that's a good class for latent process models. Let's just pick up some notation for talking about these things. We are often going to imagine that the underlying processes are going on in continuous time, but they're measured in discrete time. And so somehow modeling the latent process at the observation times is going to be more critical. So we'll mostly develop discrete time notation, and then the continuous time will come in at some point. So we have a time series model x0 to n. This is a latent process. We normally use y for the observable process. So the latent process is a Markov process model if it has the Markov property. And here we're writing the Markov property in a more mathematical form in P1. The density of xn given x1 through n minus 1 is the same as the density of xn given xn minus 1 for any n. And if there is an underlying continuous time t, we write x of t for the continuous time model, and then the measurement times are tn, and we set xn, x sub n is x of tn. And there's an extra wrinkle here, which is in P1, you see when it's defined for n is 1 through big N, there must be an x0 as well. And x0 happens at some time t0 called the initialization time. Let's think a bit about initial conditions. It's a detail that's sometimes forgotten, but it can sometimes bite you when you forget it. And so let's make sure it gets its proper attention here. We initialize the Markov process at a time t0. The initialization could be deterministic if you know exactly where the process starts at t0, if it's an experiment and you set it up exactly. It could be a random variable. In general, we're going to say x0, which is x of t0, is a draw from a probability density function fx0. And we write it like this, but we think of this as covering the special case of a fixed initial value when this density just consists of a point mass at one point. And we also think of it as covering the discrete case. We know from introductory probability that we have probability mass functions for discrete random variables, probability density functions for continuous random variables, but we can really think of a probability mass function as a density at discrete points. And so we'll just write the one density form as in equation 1 here. We'll do that for other things too. Okay, so we have the process model. It's not a process nodal. There we go. So the process model for a Markov process is defined by these so-called one-step transition densities, fxn given xn minus 1. And the Markov property asserts that the next step taken by a Markov process follows the one-step transition density based on the current state, whatever the previous history of the process. That's a slight twist on our definition of Markov process, but it's basically the same definition. And so what that means is that for a Markov model, the full joint distribution of the latent process is entirely specified by one-step transition densities and an initial value. And so it makes sense to call this one-step transition density the process model, because it's kind of the simplest way of defining the full Markov process. Now, it's an exercise in using the Markov property to just write out the form for the full joint distribution in terms of the one-step transition density. This really checks the assertion that I made on the last class that for a Markov process, the one-step transition densities define the model, because on the left-hand side of P2, we have the full distribution of the latent process, and on the right side, we have the initialization density and the product of the one-step transition densities. Now, I've left this as an exercise for you. It involves elementary rules for manipulation of joint and conditional densities and an application of the Markov property. And I think it's a good exercise to work through, just to build familiarity, getting your hands dirty with algebraic manipulation of the model class. I'm not going to go through that right now. I've set myself another question to work through, explain why a causal Gaussian AR1 process is a Markov process. So this tells you that the AR1 processes that we've been considering before in the context of ARMA models somehow fit into this situation. So let's remind ourselves what a Gaussian AR1 model is, just to set up the notation. Yn is phi yn minus 1 plus epsilon n, where epsilon n are IID normal 0 sigma squared. Okay. And part of the definition of this Gaussian ARMA process, because these epsilon n's are IID normal, in particular epsilon n is independent of y1 through n minus 1 by construction. If you want to think why that's true, we could say because y1 through n minus 1 is a function of, let's say, depending on, imagine there's an epsilon 0 that determines the initial values, then I can write it like this. And I should really use my colon notation here. So I'm going to remove these dot, dot, dots and put in the colon. Okay. And what does this mean? This means that yn given y 1 to n minus 1 has a distribution depending only on y n minus 1, not I'm not dealing with initial values very well. I told you I'll write this as y1 to n minus 2. That is our definition for yn being Markov. And here it's important that we're having a Gaussian AR1, so I'll just note that. For a general white noise process, these epsilon n's are uncorrelated but not independent. And this means that the process we get out of it is not necessarily Markov. Okay. So I want to think about time homogeneous transitions and stationarity. It'll help us think about the details of the notation and why it's set up as it is. So we have this one-step transition density fxn given xn minus 1. And I want you to notice that it can depend on n because it's arbitrary construction of xn given xn minus 1. And the process is time homogeneous if it doesn't depend on n. And that means there's some density, you could call it f, such that fxn given xn minus 1 is little f. And we'll still evaluate it at some pairs of points, which we could call xn and little xn minus 1. But now on the right-hand side of 2, that function doesn't depend on n. Now, there's a difference between stationarity and time homogeneity. And so these next two questions just ask us to think about that. So if xn is strict stationary, then it's time homogeneous. And why is that? So right, strict stationarity. Well, it's basically defined by all joint and conditional densities are shift invariant, and what this means is that if I take my xn given xn minus 1, xn given little xn minus 1, this has to be equal to f x1 given x0 xn given xn minus 1 for all n. And this looks a little bit weird, evaluating x1 given x0 at little xn given little xn minus 1, but these arguments of the density, they're just dummy variables. It doesn't really matter what you call them. So here I've called them little xn and little xn minus 1, but I could have called them a and b and it would be the same model. Okay, but the reverse doesn't hold, so time homogeneity does not necessarily imply stationarity. And the way we show that is to look for a counterexample. And here's a fairly well-known one. Consider a random walk. And we may or may not have drift. With or without drift. And let's make it a Gaussian random walk. So we'll have xn is equal to xn minus 1 plus mu plus epsilon n, with epsilon n being IID normal 0 sigma squared. And so this is non-stationary. That's particularly obvious if mu is not equal to 0 because it has a trend. If mu is equal to 0, the variance is still going up, so it's non-stationary. But it does in fact have time homogeneous transitions. And to see that, you kind of have to think about it. If you know where, if you know x n minus 1 is 23, then the distribution of xn really doesn't depend on what n is. Now we've thought a bit about the Markov latent process. We're in a position to define partially observed Markov process or POMP models. And the partial observation could mean either or both of measurement noise or entirely unmeasured latent variables. And this is really a common feature in many systems. And again, sometimes it comes true by construction, because you put in your latent process model everything that you think is underlying the system, and then the measurement model is whatever you can measure on it. And those are two different things. So we have to put together a Markov latent process model and a measurement model, and then we get a POMP model. And we're setting up a very general class of models here. And they cover many models designed for specific applications, but also the generality gives us the flexibility to develop specific POMP models appropriate to a range of applications. And even if you have a new application, you can often write down your own POMP model. So we should write down in mathematical notation what the measurement model is and what the requirements on it are. So the measurement process is a collection of random variables y1 through n, which are used to model the data y star. And so I guess our modeling assumption is that the data are like a draw from the random variable model. And yn is assumed to depend on the latent process only through the value xn at the time of the measurement. And P3 makes this assumption formal. So it says if you want to know the distribution of your observation at time n, and you're told all the other observations and the whole latent process, then you only need to know xn, and that's all the information that everything else can provide you about what yn should be. And then this thing fyn given xn we call the measurement model. Just as we had time homogeneous or time inhomogeneous process models, we can do the same thing for measurement models. In general, the measurement model can depend on n or on any covariate time series. If it doesn't depend on n, it's called time homogeneous. And in that case, fyn given xn can just be some density g that doesn't depend on n. And again, we're going to set everything up there's a lot of stuff that can be done with POMP models usefully in quite a lot of generality. So here we haven't said what the form of these models are, whether they're Poisson or Gaussian or T or binomial or whatever. But the background ideas are going to be true for all these classes of models. And in particular, time inhomogeneous process and measurement models are sufficiently common that it's worth having this extra generality. It's a couple of extra subscripts to write fyn given xn rather than just g, but it's worth it because it shows us that the framework generalizes. And we'll continue in part 2.